Look closely at the screen you're holding right now, or the nearest skyscraper window. They share an identical, invisible feature. Modern touchscreens and high-rises demand this level of microscopic flatness to function. Even a tiny variation in thickness would prevent a digital sensor from accurately registering a tap. But producing that flawless, uniform surface on a mass scale used to be incredibly difficult. Before the 1960s, manufacturing thousands of square feet of perfectly flat glass was an industrial nightmare. Manufacturers relied on what was called the plate glass method. Workers would literally cast vats of molten glass onto massive iron tables and roll it out into individual sheets by hand. This process created glass, but it didn't create flat glass. To get the top and bottom surfaces parallel, the hardened sheets had to be physically ground down and polished on both sides, a massive, inefficient expenditure of time and physical labor. As mid-century cities began designing modern towers wrapped entirely in glass, this slow, manual bottleneck threatened to halt architectural progress. Factories simply couldn't grind and polish fast enough to keep up with global demand. The solution came from Sir Alistair Pilkington, who invented a continuous, automated production line that could run 24 hours a day, 365 days a year without ever stopping. This chart shows the primary chemical recipe for the automated glass batch. The main ingredient is sand, which makes up 60% of the mixture. To that base, manufacturers add lime and dolomite to improve weather resistance, along with soda and sulfate to lower the melting point. They also add cullet, which is crushed, recycled glass recovered from the manufacturing process. This extra ingredient accelerates the melting phase and drops the total energy required to heat the furnace by up to a fifth. This highly specific batch is fed automatically into a massive furnace. Inside, natural gas combined with preheated air blasts the raw materials up to 2,800 degrees Fahrenheit. The mixture undergoes a continuous melting cycle that lasts up to 50 hours. This extensive heating period ensures the liquid glass is completely homogenized and free of any trapped air bubbles. But getting the chemistry right only solves half the problem. The factory line now has a 2,000-degree river of semi-liquid glass, and it still needs to be perfectly flattened without any human intervention. The molten glass leaves the conditioning end of the furnace and travels through a narrow canal into the central machinery of the automated line. Here is a diagram showing the core physical mechanism Pilkington designed. The molten glass is poured directly onto a highly dense bath of liquid molten tin. Because the glass is less dense, it floats right on top. Gravity and surface tension take over. The glass spreads naturally across the liquid metal, exactly like oil floating on water. This creates an absolutely flat surface where the upper and lower boundaries remain perfectly parallel. To control the exact final thickness, mechanical top rollers grip the edges of the semi-molten layer. By speeding up the rollers, the machinery gently stretches the outward spread of the glass to make it thinner. To keep the liquid tin from oxidizing and ruining the process, the entire bath is sealed within a carefully controlled atmosphere of nitrogen and hydrogen gases. Once flattened, the continuous sheet travels through an 800-foot annealing layer. An annealing layer is a massive, temperature-controlled kiln that slowly cools materials down to room temperature to prevent internal structural stresses. By using fluid dynamics instead of physical grinding, Pilkington replaced a slow, labor-intensive craft with a continuous river of flawless material. The flatness problem was permanently solved. Because the float process is continuous, manufacturers apply pyrolytic hard coatings directly on the production line. Pyrolytic coatings are microscopically thin layers of metallic oxides bonded directly to the glass surface at extremely high temperatures. These metallic oxide layers create advanced architectural products like self-cleaning windows and low-E glass. Low-E stands for low emissivity. The coating minimizes ultraviolet and infrared light passing through the pane, providing excellent thermal control for buildings. This automated technology is critical for sustainable energy. High-tech float glass provides the durable, transparent protective layering essential for modern solar panels. The impact goes far beyond architecture. By mastering this mass-produced, perfectly flat surface, the glass industry created the essential interactive canvas for modern electronics, from high-definition televisions to the smartphones in our pockets. Today, manufacturers are pushing this baseline even further with applications like selective privacy technology. This advanced switchable material adds a dynamic layer, allowing entire interior walls to shift from perfectly clear to completely opaque on demand. The glass in our windows and devices represents a decades-long pursuit of engineering perfection. It is a continuous, automated river that begins with simple raw materials and ends as a high-tech industrial foundation.